How are you guys? Tired at the end of the day? I hope not. I hope not. I'm told we are standing in between this and a Diwali party. So I'll try to get out of your way and get you on to some drinks and celebrations. So really happy to be here. Thank you all for joining. So much energy in the room and such a positive event so far. What I thought I would do is give you guys just a little bit of an idea about the journey that we've been on. A few years ago, we said we would be pursuing a strategy that we said would be a pervasive AI strategy where we would be infusing AI into all things compute, right? Ranging from the highest end GPUs in the data centers to our CPUs, with various instructions that accelerate AI, to our personal computing devices with AI PCs, where we brought a dedicated AI accelerator for the first time into the x86 ecosystem, to all things in the embedded edge environments, from 5G communications that we accelerated with AI, to NBA games, to medical instruments, to cars, and so on. So we've been on a tremendous journey to put AI into all things compute. We also knew that in order for us to be successful, we have to make software a fundamental pillar of our strategy. And we knew we could build complicated hardware, but we also knew we had to do much better with our software. And so we've been relentlessly focused in making our software better. When we introduced our first GPU products for AI that were dedicated in the late 23 timeframe, we were focused on inference. We've expanded that to a footprint in training. We have been super focused in accelerating our release cadence. I don't know if Anush is somewhere here. He's been on this mission of, I want to ship trunk every night, keep it clean, right? I see Jeff here. We've been doing a lot of work with PyTorch. So across all of the most important communities, we've been super focused on making sure that we go fast. We've also provided more and more capabilities, and hopefully you guys will appreciate it, to bring collateral, whether it's benchmarks, or whether it is richer out-of-the-box experience in terms of toolings, or day zero support for models. Like a few years back, when a model came out, you could be like, well, is this going to run on AMD or not, right? I don't feel like you have to worry about it. We have done the work. There's about 2 million models on Hugging Face, and you can be confident that every one of them is going to run. Why do we feel so confident? It's because we are doing the work behind the scenes to ensure that the regressions that we have nightly ensure that all of the backbones for these models run on AMD. So whether it is that community or whether it is all of the other communities that we are partnering with, like PyTorch, like VLLM, like SGLang, like JAX, we have been focused on ensuring that we go fast. We knew that there were going to be two important pillars. It's the open source pillar we want to partner with to go fast. ROCm, by the way, everything in our philosophy is really simple. Keep it open. We want to develop in the open. Other than the bits that are closest to metal, whether it's low-level libraries or compilers or tooling or frameworks, right? All of what we do is out in the open. And we believe that's a core fundamental philosophy. We also believed that we would partner with this trend of rising abstractions. Like, I have a PhD in computer engineering. You gave me a $150 billion transistor device. Now you see where my head is at. So it's very hard to program these devices, right? So the way to do that is nobody likes to program bits and bytes of assembly. Everybody wants to write in higher levels of abstraction, whether it's Triton or whether it's PyTorch or higher orders of abstraction. So we said we would partner with these trends, and that's served us well. But I'm actually super excited that even beyond these two fundamental trends that we are partnering with, there is actually a third tailwind that is assisting us. And that tailwind is AI is coming to automate GPU programming. There are many people who believe that, oh my God, it's so hard to write kernels, right? It is, in fact, right, very complex to program the GPUs. But the pipelines that are coming out through the latest language models to put together automated GPU programming is really changing the landscape. And so super excited that that's going to be another pillar of our strategy. So I actually have a very special guest who is in fact participating in the trends at the leading edge, whether it is partnering with the work that's happening in the open source communities, or whether it is the work that benefits from the rising levels of abstraction, or the AI assisting GPU programming. So please join me in welcoming to stage Simran Arora. Simran, thank you so much for joining us. Please have a seat.
Thanks for having me.
Yep. Simran is just graduated out of Stanford. She is an incoming faculty at Caltech and is also spending time at Together. And as I said, right, she is at the leading edge of AI software in particular. Simran, tell us a little bit about your research and how the experience has gone so far with coming on to AMD platforms.
Yes, for sure. So hi, everyone. I'm Simran. I work on machine learning and systems, AI systems. My work has traversed a couple of different aspects of this question. So one part of it has been searching for architectures that are better than the transformer and trying to understand sort of this Pareto trade-off space between AI quality and efficiency. So many folks in the room, if you are interested in AI, have heard words like Mamba and Hyena and RWKV, all these fancy architectures that are trying to maybe achieve transformer-level quality while being drastically more efficient. And at the same time, we've probably all had issues with transformer-style models. There are places where we want something better than the transformer, architectures that are better, but still not drastically increasing the cost of that. And so a major part of my work has been on characterizing these trade-off spaces with architectures such as the based architecture, which underlies things like Mamba version 2 and later versions of RWKV that have come out. Another part of the place that I spend a lot of time is on, beyond sort of this Pareto trade-off space, trying to make it easier for us as the broader community to inject our ideas into the AI landscape. So we need better open source tools, more readable, more accessible abstractions to get a broader set of participants developing on these sorts of ideas. And it's become very clear from my work, which I'll touch on a little bit more later, that co-design of AI algorithms and the hardware is really, really important to making actual progress here. So many ideas, many of these architectural ideas, algorithmic ideas have been very fast, very inspiring in quality, but not actually very fast when you go and try to run them on the hardware. So being able to help the community understand both the AI side and the hardware side has been a big part of my work. This has largely come out with Thunder Kittens, a framework that I developed during my PhD. It's been around since about May 2024, and a lot of its principles have underlined things like Mojo now and Cutlet, the Qt DSL on the NVIDIA side. But for the past 4 months, we've been actively building out Hip Kittens, the AMD version of Thunder Kittens. And so I'm really excited to tell you about what we've achieved there.
Yeah, actually, tell us actually how did you get started on AMD and what is Hip Kittens and how did you name it?
Yes. So CUDA is on the NVIDIA side. Hip is the equivalent on the AMD side. So hence Hip Kittens. Can go into longer detail about why kittens, and why Thunder, and all the others, but that's the TLDR. So very honestly, I was on the job market for faculty for many months, and I was like, talking about old work. I was like, I just need to sit down and code. And at the same time, I was very annoyed that there was just one hardware that kept cropping up in all of the papers that I read. And I thought, one of the most important issues to be working on right now as an AI researcher is how can we open up more hardware and more compute, understand whether other paths are possible, especially because I think that the hardware really constrains the types of algorithms that we can unlock. So I thought, why not just sit and rebuild all of Thunder Kittens, but on something that's open source and that has the potential to address those concerns of mine. So I actually had never programmed or used an AMD GPU before then. By the second week, I bought a ton of AMD stock, which I'm now very happy about. And then I was like, this is going to work. This is going to work. And now it's, we have, so we're going to release this in the next week and a half, hip kittens, but we have peak performance kernels, so comparing to kernels that have been handwritten in assembly by AMD's own engineers for workloads like attention, for FP8 gem, for FP6 gem, for all different types of workloads, backwards passes, forwards passes, and with very, very readable, modifiable, single kernel. If you're familiar with Thunder Kittens, exact same outcomes there. Very concise scheduling patterns for these kernels. We're able to get peak performance and even performance that's very exciting given the competitive NVIDIA devices that are out there and our experiences, say, using Blackwell and so on.
So based on all the work that you've done so far, right, there's this notion that, hey, you need to have thousands and thousands of kernel engineers to be productive, and it's this big moat. How do you think of that based on your recent research?
Yeah, great question. So I think one anecdote here is that Together AI, for instance, a company that the entire kernels team is using Thunder Kittens to write every single kernel within the company. It was very evident that better abstractions can unlock much, much faster speeds of iteration and more competitive landscape here. So when we looked maybe 2 years ago at what was being used for some of the inference stack, we have Flash Attention 3. Very, very fast, exciting algorithmic kernel. But when DeepSeek came out with MLA, when all these different types of attention variants came out, it fell on 2 engineers, people at Colfax, not even internal to our company, to go and try and understand how do we modify this kernel, how do we fix it, how do we get up to speed. That was an extreme bottleneck in the pipeline where the code was just entirely unreadable. It spanned 15 different files, 20 different files. We didn't know how to, it took weeks to modify it. Now, turning to Thunder Kittens and these sorts of abstractions, it really allows a broader set of people to participate in kernel development and also makes it so that we can quickly modify the ideas that have already been there to support new ideas in AI very, very quickly. And so the entire team turned to using a framework like using Thunder Kittens. Cursor now uses Thunder Kittens. But broadly, I think that this question of the software moat is alleviated if we move towards better abstractions that are more readable and more easily modifiable as AI progresses.
Super exciting. We absolutely subscribe to that philosophy and all the research ideas that you're bringing forward. Now, if you fast forward along the same vector, the next frontier, in my humble opinion, right, is AI assisting the GPU programming. And you've done some work there. You've also published Kernel Bench to actually evaluate how good LLMs are for AI generation. Would love to hear your thoughts on that topic.
Yes, for sure. So I think there are sort of 2 forks in the road here that I see for kernel generation. So to start with sort of where we are right now from a lot of the Kernel Bench evaluations that we did. And for those not familiar, Kernel Bench took a bunch of these open source and closed source leading models and went and evaluated how well they performed on a suite of 250 different kernel workload problems. We used techniques like parallel generation, iterative generation, kind of leading tips and tricks from the community. And we found that the kernels were quite brittle. In some cases, it was, there's signs of excitement out of these models, and it'll definitely work eventually. But at the current state, the models really struggled to use the leading hardware features, most recent features, things like maybe TMAW, GMMA on the NVIDIA side, or direct to LDS, pieces like this on the AMD side. And so that bit of being able to keep up with the cutting edge was really lacking. And the readability, the use of abstractions, the modifiability was lacking. So I think there's 2 forks. Do you care about readability, modifiability, assisting a human, or do you care about pure peak performance? And I have a little bit to share on what I think progress here could look like for either. So if you just care about peak performance, think there are many levels in the stack of kernel generation. There is using Triton, there's using HIP and CUDA. There's the HIP-CC compiler in the middle, which has probably been my part that I would want to avoid if I were writing peak performance kernels here, and then there's raw assembly. So I view a world where we have models that are just literally writing raw assembly, discovering the peak performance kernels, and not getting, we're not putting in anything that gets in the way of that peak performance in any which way. This will look like, kind of brute force search, being able to understand the patterns of assembly that work well, and really have no compilers in the way at all. This has been very, very evident from my experience using AMD as like a place where I think it would be exciting for models to just go and directly write assembly. On the other end of the spectrum, we want models that can assist humans. So by week 1 of me working on this AMD Hip Kittens project, GPT-5 and Claude were, say, here in their level of understanding of the hardware and GPU programming. I knew about GPU programming, but my knowledge of the hardware was here. By week 1, by week 2, I was at par, and by month 3, month 4, we're here, and GPT-5, Claude are still here. We need frameworks that can become more dynamic, that can understand my goals and my context, and every single day when I wake up and I'm writing yet another kernel in AMD, in abstractions that I think are readable and more modifiable and more friendly, like Hip Kittens, the model actually goes and starts learning with me. And I think that this world looks like it will capture a lot more of the exhaust from kernel engineers, kernel programmers, the specific goals that they're after when they're going and trying to write a kernel. It's not just going and taking a final end state kernel that's on the internet and maybe gets peak performance, but it's really about taking that whole process of what are all the optimizations I tried, what are the conversations I had with AMD engineers, what are the sections of the CDNA ISA guide that I read, and what are all of these experiments that I tried and what worked and didn't work, and how do we turn all of that exhaust into trainable data? So I think that data collection bit, I'm super excited about people solving. I think there are companies, GPU mode, companies like this looking at collecting those traces that will help the kernel generation process going forwards.
Wonderful.
Yeah.
Thank you so much, Simran. Super excited to partner with you and looking forward to all the research that will come along.
Thank you so much.
So as you just heard, right, there is a growing community of kernel developers on AMD platforms. So we've had actually a contest run here in parallel with this event, and I would like to invite our next guest on stage. I keep doing this. Hopefully this will, another page. There you go. I seem to get the latency exactly right. Can somebody do this in the back? Here we go. Yes. There you go. Mark, please come on stage. Thank you. Yeah, Mark, many of you need no introduction to him. He's very well known as one of the core folks behind PyTorch, and has done a tremendous amount of work in the open community, and is the creator of GPU mode, which my understanding actually was, it was not GPU mode some time back.
It used to be CUDA mode.
There you go.
That's right, yes.
Happy to change the name. Mark, actually, super excited with what we have been able to do together with the kernel contest. So tell us a little bit about sort of what happened the first time around and now.
All right, yeah. Thank you, Vamsi, for the nice intro. But yeah, so for context, folks, the sort of problem we were looking to solve was we wanted to train an LLM to generate like good kernels for GPUs, because we just figured there's like very few kernel programmers that we can find at Meta, very few in open source. And so we were thinking, okay, like, can we have some sort of mechanism of like getting people in the open source, like competing on kernels and like picking the best ones? So this was like a purely open source project. Like it was started with like some people I met like from GPU mode, like Mate, Eric, and Alex, who isn't here, but Mate and Eric are right there. You can wave if you like, yes. And what was cool is like initially when we started off with the idea, we're like, well, this is cool. Like maybe we'll get like a few hundred kernels out of this. Maybe they'll be high quality. But very quickly we learned that like, after our first competition, which we did designed with folks from the AMD China team, like George and Daniel, we learned, okay, well, it turns out after a 2-month competition on just AMD hardware, we generated more permissively licensed data than GitHub has in its entire history for NVIDIA. Yeah, so it just goes to show you, like, there's just like very, very little data, right? And so one of our prime motivations for thinking and designing about these problems is we want problems that people like care about. Like, as in, we want problems where if you're at the top of the leaderboard, it like matters, and AMD's happy giving that person the prize money. So the first set of problem we designed around like compute-bound kernels that show up in DeepSeek. And the second set of kernels we designed were around like optimizing communication kernels, which are becoming insanely important. And even though communication kernels are a lot more niche, like it just smashed any sort of usage numbers we saw before. So we're like, thrilled to work with you on it.
Yeah, my understanding is we had like 2,000
submissions a day, yeah. Just pure on only just like AMD comps kernels, yes.
It's amazing, yeah, super excited. And the quality of kernels that some of the team was commenting was, right, one of the best that we have seen. So very, very nice. So maybe a little bit more detail on actually what the kernels were and what did the contestants actually do?
Yes, all right. So, but before I answer this, like, I think one really important thing I think that's like under stressed is like often when people talk about like the CUDA moat, they don't keep it. They often think of just like the CUDA software, but I think the CUDA moat is also like the CUDA developers, as in the best CUDA developers in the world are not necessarily working at NVIDIA. They're like folks working at AGI labs. They're folks like working in open source. So again, like we wanted like important problems. And so for these problems, we designed 3 kernels that show up in like MOE models. The first one is an all-to-all kernel. The second one was a fused gem-reduced scatter. And then the last one was a fused all-gather and gem. So all of these like show up in MOEs. Like MOEs have like much more like dynamic routing decisions. If you look at like modern kernels, they don't look like, like I add 2 vectors to each other. They're not like, they don't look mathy anymore. They look very scheduling heavy, as in like you're often thinking, okay, like this compute unit is going to be doing comms, and it's next to this other compute unit that's doing like compute, and like and you segment that, and like okay, well some kernel like some parts of the kernel are doing this, some parts of the other kernel are doing that. So like it often involves like a lot of like interesting like scheduling decisions, and so when we saw like kind of the important tricks that people used, often it was basically really understanding the specific constraints of the hardware, as in like how big are the caches and like what can you fit in them. The others, for example, were just like using libraries that were newer. Like for example, AMD has a very nice new comms library called Iris, which is a Trident-based communication library. So the winner of the fastest entry in the gem-reduced scatter, for example, just like used that with some other like simple tricks using like IPC. So it was all quite nice in that if you look at a lot of the top kernels, like they often included a bunch of algorithmic innovations in how you set up your PyTorch code, how do you like launch your process, how do you like pre-compile certain like auto-tuning configs, but also like leveraging like libraries like Iris, leveraging like HIP IPC, and it all just sort of worked just because like as long as it's a kernel, like the individual kernel can be in whatever language you want. So this has been like one of the big points of diversity and why I feel very happy that we renamed our server from CUDA mode to GPU mode, just because like most GPU hackers are not like necessarily just using CUDA these days. They're using like Trident, they're using HIP, they're using Thunder Kittens. And I think it's so healthy. Like people sometimes are like, oh, like there's too many choices. No, it's great that there's a lot of choices, which means that like we're gonna have like much stronger incentive for the best technologies to be open source.
Yeah, that's actually like music to our ears, right? I mean, the whole idea of us partnering so closely with the open source community is to help realize that vision that you outlined. Maybe tell us a little bit more about your thoughts for the future. Where do you want to take these kind of efforts and the collaboration?
Yeah. So I think like our broader mission in GPU mode is to make GPU programming more accessible, right? And so like I think there's sort of a few very good techniques for this. Like one is like what I would call like traditional tooling, which is things like compilers, like programming language. Like this is the kind of stuff that like we do in PyTorch and is our bread and butter. And I think a lot of the focus should go there. I think the other one, of course, is like basically accept this assumption that like there will always be variety in the kinds of kernels that you have, that like you could have very hardware heterogeneous tools, but you could also, if you include more people, do the sort of bare metal performance because you just can scale over more humans as opposed to purely better tools. So yeah, I absolutely, I think, want to be doing more competitions. Of course, now, like, I think comms kernels is one thing that I think is like a very obvious gap where, like, comms kernels are kind of like okay in PyTorch. Like, and Triton, they don't really have something first class in it. Like, they have like Triton distributed, which is like maintained by folks at ByteDance. Like, there's like Iris at AMD. So I think there's sort of like a lot of like opportunities there for building some like best-in-class tools, more examples of like full models that were like built this way with like the right libraries for it. So yeah, I mean, I'm super bullish, and if anything, like I think like a lot of hardware vendors should sort of like accept that, like, hey, like on average, like maybe like a very like at a hardware vendor, like an average hardware vendor is going to be better at kernels than the average person in open source. But I don't think this is true if you look at the peak. Like if you look at like the best kernel hackers, like they tend to be in open source and AGI labs, and I think figuring out more ways of engaging with them, to me, is the right strategy. But yeah, I think AMD is doing a good job here in the sense that, like, all of the kernels we published are open source. People often write write-ups. They're very good. You can go like learn very state-of-the-art stuff. You can like run the numbers. You can reproduce them. So yeah, I think teaching more people also about like reliable benchmarking is kind of like a common foot gun. Teaching people like the nuances of how to schedule hardware differently. And just like going very deep with people, like as opposed to sort of like delegating things behind compilers. Yeah, for what it's worth, like maybe some people are going to the Triton conference tomorrow.
Tomorrow, yeah.
Yeah, what's interesting is like even the Triton team themselves is now sort of accepting that like you need libraries that are a bit lower level. So things like Gluon are becoming very popular.
Yeah.
And I think it's much easier to build low-level libraries that are popular if you basically teach people how to do the low levels. Otherwise, your audience and your customers won't be as sophisticated, and then things will just be slow. So I think this is why like this work we're doing with communities is just so crucial.
So exciting with all the activities, and super happy to partner with you, Mark.
Oh, thank you, Vamsi. Appreciate it. Thank you.
Okay, so I guess it's been a long day, so let's try and wrap this up here. So I want to close by telling you guys a little bit about where we are headed at AMD. What you can count on is that our roadmap is accelerating. We are, as you know, in our 350 generation of product, and we have an extremely aggressive set of plans to be able to ramp the 350 product. And then we are super excited by what's coming next with our 450 generation of product. So we're on this cadence of rolling out our product roadmaps. And then our commitment to these strategic initiatives on the software is going to be very, very strong, right? We're going to be deeply partnering with the open source communities. We're going to be really promoting the levels of abstraction that help make people become much more productive. And then finally, we're going to have a lot of internal activities, but also promote external collaborations to have AI help GPU programming. So you can look forward to a lot more things along all of these vectors. And for all the support, for all the learnings, and for all the teachings that you have given us at AMD to bring us from where we were a couple of years ago to this stage, thank you sincerely. We are super, super grateful to be a humble part of the community and provide choice to the industry. And you can be certain that I really feel passionately that we are right at that inflection of the next big thing that's going to happen in AI. And let's go do it together, all of us. And for all of you that are here, a small token of thank you from us. We wanted to put a little bit of GPU currency in your pockets. So here is a little coupon that you can go use it at our developer cloud, and hope you enjoy the little party that we have afterwards. Thank you for coming.